Figure shows the variation of a force F acting on a particle along x-axis. If the particle begins at rest at x is equal to 0, what is the particle's coordinate when it again has 0 speed? The given options are x is equal to 3, x is equal to 6, x is equal to 5, and x is equal to 7. Well, what's the data given to us? There is a particle which is acted upon by a force F, which is variable. We also know that the particle begins at rest at the origin, x is equal to 0, and there is a moment where the particle again has 0 speed. What do you mean by that? It is at rest at that moment. So we need to calculate the particle's coordinate when that happens. So how do I relate this data given with the graph here, which gives us the variation of the force applied and the x coordinate of the particle? The key here is the work energy theorem. What is work energy theorem stating? It says that the net work done on the particle must be equal to the net kinetic energy change brought in the particle. And we know for a fact that the particle is at rest in the beginning and is at rest at the end. So what is the net kinetic energy change of the particle? 0. So what? How do I relate that data with the graph here? Well, we know that the area under the curve of force versus the x coordinate of the particle graph is giving us the net work done. So we need to calculate the x coordinates such that the net work done within this interval must be equal to 0. And for that, we will consider the area above the x-axis to be positive, which corresponds to the positive work done, and the area below the x-axis to be negative, which corresponds to the negative work done. But put together, they both add up to give you 0. All right. So let us consider the interval. We know that from x is equal to 0 till x is equal to 3, it is positive work done. So it is positive area. Let's calculate that first. It must be equal to the sum of area of the square here, which will be 10 joule, and the area of the smaller triangle here, which will be 5 joule, and the area of the bigger triangle here, which is 20 joule. All right. So what is the positive area put together here? This is 35 joule. So this area or the work done here, call it W1 if you like, it is plus 35 joule. We need to look out for an equivalent negative area on the lower side or below the x-axis, which corresponds to the negative work done. Do you see a similar structure here below the x-axis as it was above the x-axis? I think we do. Look at this interval, x is equal to 3 till x is equal to 6. This structure here is very much similar to what we found here. And the units on the scale chosen are simply the same. So this negative area must be equal to minus 35 joule in magnitude. Basically, this is negative work done. What does this mean? 35 plus minus 35 will give you 0. So the work done all the way from the coordinate x is equal to 0 till x is equal to 6 add up to give you 0. So I can write till x is equal to 6, from x is equal to 3, you get the negative area or the negative work done to be minus 35 joule. So the answer we need is x is equal to 6. That's the coordinate where the particle comes to rest once again. The correct option for this question is B. If pulleys shown in the diagram are smooth and massless, and A1 and A2 are acceleration of blocks of mass 4 kg and 8 kg respectively, then find A1. All right. We have two blocks, 8 kg and 4 kg. All the surfaces given here are smooth, no friction anywhere. Why do the 4 kg and the 8 kg blocks move in the first place? It's because there is gravity acting on 4 kg block in this direction, which is greater than the tension in the string connected to it in the upward direction, thereby making the 4 kg block move in the downward direction. This string passes over these two pulleys and this movable pulley moves in this direction. Do you see that 8 kg block is connected to the massless movable pulley? In that case, the displacement, velocity and acceleration of 8 kg block is as good as that of the movable pulley, both in magnitude and direction. This is why they move. We are supposed to find the acceleration of the 4 kg block. In order to do that, let's look at each block one at a time. Let's take 8 kg block. Which is the force acting on it on the horizontal in order to make it move? It is the tension in this string connected to the 8 kg block. Let's do one thing. Let's choose x-axis and y-axis like this. We will take the displacement, velocity and acceleration along the positive x-axis and positive y-axis to be positive, and we will take displacement, velocity and acceleration along the negative x-axis and the negative y-axis to be negative. In that case, for the 8 kg block motion, application of Newton's second law will give us 2t equals 8a2, or t is equal to 4 times a2. Call this equation number 1. Do the same thing for 4 kg block. Apply Newton's second law for its motion. It will give us 4g minus t equals 4 times a1. Call this equation number 2. What do we need? We need a1. But there are 3 variables, a1, a2 and t. How many equations have we got? Only 2. We certainly need another equation. And how do I get that? This is exactly where the constraint equation concept becomes helpful. How do I get the constraint equation? What is constraint equation? It is an equation relating the acceleration of 8 kg block and the 4 kg block. How do I do that? Well, the string diagram becomes helpful for that. What is string diagram? Simple. Look at the string shape in the beginning. Draw the diagram. This is how it is. This is the free end and this is the fixed end. Do you see that? When 4 kg block moves in the downward direction, this end, the free end here, also moves in the downward direction. Let's say by a distance x. These 2 points here are the diametrically opposite points on the movable pulley, and this distance is half the circumference of the movable pulley contour. When the free end comes down by x, do you see that the movable pulley moves to the right, let's say by a distance y. So these 2 points here will also move by a distance y, and they come to this position. What is the new string diagram? It is like this. Now, how does it help? Simple. We will look at the string length gained here, which is x. It must be because the string length y and y is lost on the other side. And that's because the string is inextensible. So we have a relation between x and y. What is it? X is equal to 2y. How is this helpful? Simple. X is the distance moved by the 4 kg block and y is the distance moved by the movable pulley. Movable pulley and 8 kg block are connected by a string. So the distance moved by the movable pulley is also the distance moved by 8 kg block. So we have got a relation between the displacement of 4 kg block and the displacement of 8 kg block. Let's say we differentiate this once with respect to time. What do we get? we get dx by dt equals 2 times dy by dt. What is dx by dt? It is the variation of position of 4 kg block with respect to time. That's the velocity. So we have got the velocity of 4 kg block on one side. That's equal to 2 into what is dy by dt, the velocity of the movable pulley, which is also equal to the velocity of the 8 kg block. So it is V2 here. Now, differentiate it once more and you get the acceleration. You get A1 is equal to 2 times A2. A1 is acceleration of 4 kg block and A2 is acceleration of the 8 kg block. Finally, we have got the third equation. What is the third equation? A1 equals 2 times A2. Call this equation number 3. Let's clear this. What do we need? The value of A1. Now from these equations, let's solve to get A1. Take the second equation. We have 4g minus t equals 4a1. We can write t in terms of a2. So we have 4g minus 4a2 equals 4a1. We want only a1, okay? We will eliminate a2 now. a1 is equal to 2 times a2. In that case, we get 4g minus 2 times a1 equals 4a1. Here we have it. Solve this and you get a1 is equal to 4g by 6 or 2g by 3. So the answer we need, which is the acceleration of 4 kg block, happens to be 2g by 3 meter per second square. The correct option for this question is B. Find the acceleration of the two blocks of mass 4 kg and 5 kg if a force of 40 Newton is applied on 4 kg block. Friction coefficient between the respective surfaces are shown in figure. You may take acceleration due to gravity to be 10 meter per second square. All right. What's the data? There is a 4 kg block sitting on top of 5 kg block. We have the coefficient of friction for the pair of surfaces as shown in the figure. There is an external force 40 Newton acting on 4 kg block and we need to find the acceleration of these either blocks. First of all, do we know for sure that these two blocks are moving separately or together? We don't know that yet. So the best way to solve this problem for the acceleration of the blocks is to consider in the beginning that these two blocks put together as a system have a common acceleration A. With the knowledge of that A, let us find the frictional force acting between the surfaces of the 4 kg block and the 5 kg block. If that frictional force happens to be well within the range of the static frictional force possible between the two surfaces, then wonderful. It is a system of 4 kg and 5 kg moving with a common acceleration A. If not, we need to consider the fact that 4 kg and the 5 kg block have different accelerations. Let's proceed. Here is the system of 4 kg and 5 kg block with our assumption that this system is moving with a common acceleration A. In which direction? Let's say in this direction along positive x-axis. Well, the friction between the 4 kg and the 5 kg block surfaces is internal. And what we need is only external force to consider the system's motion. Which are the external forces? There is 40 Newton in this direction. And there is friction between the 5 kg block lower surface and the horizontal surface here. And it's in this direction. So, application of Newton's second law will give us F minus small f equals 4 plus 5 into A. Now, what is F? 40 Newton minus what is the friction acting between the surfaces of 5 kg block and the horizontal surface? We know the value of mu. Let's find that first. F is equal to 0.3 into 4 plus 5 into 10. And that gives us 0.3 into 90 or 27 Newton. So from here, this is 27 Newton and that's equal to 9 times A. Solve this, you get A to be 13 by 9 meter per second square. What is A here? It is with our assumption that the system has a common acceleration, correct? So that common acceleration happens to be 13 by 9 meter per second square. Now let's find the friction between the 4 kg block and the 5 kg block with this condition that the common acceleration is 13 by 9 meter per second square. How do we do that? Newton's second law again. For this 4 kg block with this as x-axis, we know that the external forces are 40 Newton in this direction and the friction between 4 kg and 5 kg block surfaces F2 in the opposite direction. Now, F minus F2 will give us 4 into 13 by 9 or F2 will be F which is 40 minus 13 by 9 into 4. Now, when you simplify this, you get this to be 34.22 Newton. Now, let's find the maximum static frictional force possible between the 4 kg block lower surface and the 5 kg block upper surface. What is it equal to? Well, it is F2L, which is equal to mu. What is mu there? 0.5. That into the mass into acceleration due to gravity, which will give us 20 Newton. Do you see that the maximum static frictional force possible between the surfaces of 4 kg block and the 5 kg block is just 20 Newton? And what is the friction we calculated with the common acceleration assumption? It is 34.22 Newton. So, what's the conclusion? This combined motion is not possible. We have to consider the fact that 4 kg and the 5 kg block are moving separately with their own accelerations. So, let's calculate those accelerations. Here is the 4 kg block. Which are the external forces acting on it? 40 Newton in this direction and F2 in the opposite direction. If the acceleration of the 4 kg block is in this direction, let's call it A2, then application of Newton's second law will give us F minus F2L equals M2A2. What is F? 40 Newton minus F2L. We just calculated that it happened to be 20 Newton. And that's equal to 4 times A2. So A2 turns out to be 5 meter per second square. This is the acceleration of the 4 kg block. Now let's look at the case of 5 kg block. Which are the external forces acting on the 5 kg block? There is a force of friction acting between the block surfaces F2 in this direction. How much is that equal to? It is equal to 20 Newton. And there is a force of friction available here between the lower surface of the 5 kg block and the horizontal surface. Let's call it F1. And we also know what is the value of this F1 max. It happened to be 27 Newton. Do you see that the driving force 20 Newton is less than F1 max, which happens to be 27 Newton? What's the conclusion then? This block, the 5 kg block, will not move. So the acceleration of the 5 kg block is 0 meter per second square. Then, which is the correct option for this question? It is C. Next, we have a question with options based on two statements. First, the data. If two springs S1 and S2 of force constants K1 and K2 respectively are stretched by the same force, it is found that more work is done on spring S1 than on spring S2. Now, statement number 1. If stretched to the same extension, work done on S1 will be more than that on S2. Statement number 2. K1 is less than K2. Here are the options. Option A. Statement 1 is true. Statement 2 is true. Statement 2 is not the correct explanation of statement 1. Option B. Statement 1 is false. Statement 2 is true. Option C. Statement 1 is true. Statement 2 is false. Option D. Statement 1 is true. Statement 2 is true. And statement 2 is the correct explanation of statement 1. Let's understand this. There are two springs with different force constants, K1 and K2. What do you mean by they are stretched by the same force? It means that in both the springs cases, you have the same amount of force being applied, which means that the restoring force in both the springs in magnitude is the same. Are the stretch the same in both spring 1 and spring 2? Need not be, because K1 and K2 are different. And it is found that more work is done on spring S1 than on spring S2. Let's understand this even better with the diagram here. This is spring number 1 with spring constant K1, and this is spring number 2 with spring constant K2. The force applied on both these springs is simply equal to F, which means that the restoring force in the spring number 1, which is K1 x1, must be equal to the restoring force in the other spring K2 x2. What are x1 and x2? The stretch in the individual springs respectively. We also know that the work done in the case of spring 1 is greater than the work done in the case of spring 2. So W1 must be greater than W2. It is given in the data. Then we can write W1 by W2 to be, what is work done on a spring, by the way? Half kx square. And in the first spring's case, it will be half K1 x1 square. And in the second case, half K2 x2 square. And we know that this is greater than 1. Half and half can be cancelled. From here, we can also write K1 by K2 equals x2 by x1. Do you see that K1 x1 must be equal to K2 x2? So using that and simplifying this, we get x1 by x2 to be greater than 1. Look at this. We have x1 by x2 equals K2 by K1, correct? In that case, K2 by K1 is greater than 1 as well. Now look at the statement number 2. What did the statement number 2 say? K2 is greater than K1. What did we get? K2 is greater than K1. So the statement number 2 is correct. Now let's look at the statement number 1. What was it? We are supposed to stretch both these springs by the same extent x. And we are supposed to compare the work done in both the springs. If the stretch is same, we can write the work done ratio to be W1 by W2, and that's equal to half K1 x square by half K2 x square. X is same, right? That's why. You can cancel half, you can cancel x square. So you get this ratio to be K1 by K2. But you know that K2 is greater than K1. So this ratio must be less than 1. So The work done in the case of spring 1 is less than the work done in the case of spring 2. Obviously, the statement 1 is false. Which is the correct option then? It is option B. Shown in figure is a loop-the-loop track of radius 10 meter. A box starts sliding from a platform at a distance h above the top of the loop and goes around the loop without falling off the track. Find the minimum value of h for successful looping. You can assume that the friction is negligible at all surfaces. Alright. What do you mean by loop-the-loop track? It means that if the block slides down, there is a path available for the block to go along the vertical circular motion. We need to find the minimum value of h for successful looping. Do you see that the more the value of h, the more the speed gained by the block when it reaches the bottommost point here of the vertical circular path, and more the probability of the block completing the vertical circular motion itself. We are supposed to find the minimum value of h such that the block completes the vertical circular motion. What are we looking at? We are looking at just completing the vertical circular motion case. And we know that to complete the vertical circular motion, to just complete it, the minimum speed needed by the block at the bottommost point happens to be square root of 5 g into radius of the circular path. Radius is given to us, 10 meter. How do I find a relation connecting this h and the radius then? Simple. You can apply mechanical energy conservation principle. We know for a fact that all the surfaces here are smooth and there are no non-conservative forces in action or doing any work. In that case, mechanical energy is conserved. So look at the motion of the block from point A till point B and apply mechanical energy conservation principle. So for this point to this point, considering datum to be here, where we define the gravitational potential energy to be 0. This is the only potential energy needed in this case. All right. So the sum total of potential energy and kinetic energy must remain the same. Look at point A. Its height with respect to this point B is h plus 2r. So what's the gravitational potential energy? mg into h plus 2r for the block. What's the kinetic energy? It is at rest in the beginning, so 0. Now at B, the gravitational potential energy is 0 and the kinetic energy is half mvb square. You can cancel m. So you get g into h plus 2r equals half into what is the minimum speed required by the block so that it can just complete the vertical circular motion? It is square root of 5 gr. Substitute that here. You will get half into 5 gr. We can cancel g as well now. Let's simplify. You get h is equal to 5 into 10 by 2 minus 2 times r value is 10. So what is it? 50 by 2, which is 25, minus 2 into 10, which is 20, or 5 meter. So what is the minimum value of h required so that the box can slide down and just complete the vertical circular motion? It is 5 meter. The correct option for this question is A,